Bismillahirrahmanirrahim. Assalamu alaikum viewers and welcome to my channel, and in today's video we'll just try to learn how to reduce a non-exact first order differential equation into exact form by using rule 2, because in the previous video we learned rule 1 quite exhaustively along with its relative example. You can see the link in the description box. Also, we can see the video involving how to solve simple exact ODE. It is also mentioned in the description box below. So we know well, those who have watched already my videos, previous ones, we have studied quite deeply how exact ODE of first order looks like. It looks something like this. We know that quite well. And we know well how to evaluate this differential equation and how to obtain the solution definitely in the form of a function. But if, for instance, we just say that this thing, which is actually the partial derivative of the function with respect to x, and n is the partial derivative with respect to y of the function f in the exact ODE, if they are not expressed in the exact they are not expressed in the form of partial derivatives, then definitely they are not going to satisfy this condition. They're not going to satisfy this condition if they are not the partial derivatives. Then it means that this equation is not exact. I mean, it is non-exact ODE. Then how to reduce this thing? If we use rule 1, and if rule 1 is not helping us out in obtaining the integrating factor, then we are definitely going to move to the rule 2. We'll try to use that thing, because integrating factor is an entity that is used to convert non-exact ODE into exact form. Okay, and we represent that integrating factor in the form of a mu. We use a Greek notation mu here, and we multiply the entire non-exact differential equation with that integrating factor, which later turns into exact form, and then we are going to use the same strategy that we use for the exact equations to solve. Okay, so what is the way of obtaining integrating factor with the help of rule 2 if the rule 1 is not helping us out? Then for rule 2 says the strategy that we have to follow in the rule 2. We are going to use this thing. We just take the x derivative of this partial derivative of the function f. It's not basically partial derivative because we are dealing with the non-exact thing. So we are going to differentiate this n thing with respect to x, and we are going to differentiate this m function with respect to y. We'll subtract it, and then we divide whatever we obtain by m. Okay, that's what our rule 2 says. Okay, my pen is not working. Oh, it's the one that my student gifted me. Okay, so when we use this strategy, the rule 2 strategy, and if we just get a function involving simply variable y, we represent that function with our q. In the rule 1, whatever we obtain through rule 2 method, we represent that by p, if you just watch that video. But this time we are going to use different notation. Okay. Chest infection. Okay, so when we get this q, which is actually some kind of function, let us just represent it what shall I use the notation? Capital F, how about that? And it is something going to be like this. So this q will help us in obtaining the integrating factor that is going to be represented in this form, mu of y, because over here the variable that is so involved is simply y, so the integrating factor also contains nothing but y. So it is mu of y. So how this mu of y is going to be obtained? We are having full theorem behind, but we are not going to discuss this thing. The only thing that I would like to assert here, that this integrating factor mu of y, this integrating factor is the solution of this first order differential equation. And how it comes, we are having an exhaustive theorem proof at the back. We are not discussing this thing right in this video. So okay, so with the help of this equation, we are going to get this integrating factor, and once when we get it, we multiply entirely with this non-exact ODE, we turn it into exact form, and then we are going to use the entire strategy that we used to solve the exact ODE. So let's move ahead and try to see an example here. For instance, I'm having a question. Okay, so this is the beautiful question here. We can see that if we just try to compare our given question with the general form of exact differential equation of the first order, we see that our m is 1 here. Okay, m of xy. I'm just simply using m notation here. No need to get confused in that. So n of xy is this. Okay, so let us check whether it is exact or not, because definitely we are in learning phase. We should be very exhaustive in our work. So let us try to perform a check work. So let's see, is it partial derivative of the function f with respect to x? If it is like this, and this is the partial derivative of function with respect to y, if it is like this, then it should satisfy this condition. It should satisfy this condition, or it should satisfy this thing. Alright? It should. Let's see, is it satisfying or not? It's quite visible it's not going to satisfy, but we have to show the work. Okay? Let's differentiate this stuff with respect to y. Obviously it is going to give me 0 here, and I will differentiate this thing with respect to my x, so it is giving me 1 upon y, and that's it. So you can see that f of xy, which is actually this, it is not equals to f of yx, which is this. They're not equal. So it means our equation, the given equation, is not exact. We have to convert it into exact form. So we are going to use here rule 2, because I told you already that once when you are going to get such kind of questions in your exams, you have to apply all the rules. So once if you just apply rule 1 and you're not going to get a function involving simply x, you are definitely going to verge towards rule 2. So I'm just directly moving to rule 2 because this video is entirely rotating around this concept. Okay, so let us use rule 2 here, because rule 1 is definitely not going to give you the integrating factor. So we just jump to the rule 2. Alright, and first of all, let us find out nx and then my 1 by 1. So our m is this, our n is this. Let us find out nx, which is actually the partial derivative of n function with respect to x. So whenever you know well that whenever we just try to take the partial derivative, we consider the other variable as a constant. So that's an understood thing. So once you are having strong grip in performing the differentiation work, so we just directly write down here the answer. So it is 1 upon y. That's it. Now let's find out m sub y, which is actually the partial derivative of m with respect to y here. And here my m is nothing but 1, so it is going to give me 0, because constant number, constant rate, definitely the rate of change of a constant process is 0. We know that. Okay, so now rule 2 says that once when we subtract my from our n of x and sub x, and we divide it with our n, what we get? We get 1 upon y minus 0 upon 1 is giving you nothing but 1 upon y. But this is a function involving simply y that we call q. Alright, and now we just got our q here. Okay, so now what next? Let's find out the integrating factor. And integrating factor is so obtained through this process. This equation on solving going to give you mu of y. So here, I'm sorry, it's mu. I'm extremely sorry. So it's this. This mu was looking a bit clumsy, so I just used the remover word here. So okay, so this is my 1 upon y times mu. Okay, let's perform a method of separating variable. You can also see the related video of solving ODE through method of separating variable in the description box if you want to. Okay, so once when we shift the things here and there, you're going to have a form like this. Then we integrate both sides like this. We are going to have ln of mu plus some constant into ln of y plus some constant. So I just move this constant over there. Both constant get subtracted. Once again, I'm going to get some constant. Okay, so I'm not going to mention that constant here. Okay, so it's not basically relevant here. So now in order to remove this natural log at both sides, we just try to apply here the anti-log of which is actually exponential Euler number. So we just apply here anti-log of this natural log, which is exponential, this thing. This anti-log is going to cancel out the effect of the natural log, and we are simply going to get this. Okay, so this is mu of y actually, but this is my integrating factor. Okay, now the integrating factor is so obtained. We are now going to multiply our equation, which is given in the question, entirely with this integrating factor, and we will turn it into exact form. Okay, so we can see here that this was my question. Okay, so now I'm going to multiply this entire equation with my integrating factor, which is y. Okay, so it looks y dx plus y times x upon y minus sine y dy equals to 0. So it looks y dx plus x minus y sine y dy equals to 0. Okay, so now this is my m and this is my n. Okay, now let's take the exactness here. Okay, take the derivative of this m with respect to y, take the derivative of this n with respect to x. They should be equal, and definitely they're going to be equal. So you see my is giving me 1 here, and nx is also giving me 1 here. I'm trying to do it quite directly because now the thing is quite clear. So now it is equal. So equation is now exact. Now this is an exact ODE. Now let's perform the process of evaluating or solving exact ODE. So what we do, this is our m, which is, it can also be expressed like the partial derivative of the given of the function that we are going to obtain with respect to x. That is our m. Okay, so m is actually the partial derivative of the function that we are going to find that's going to behave in the solution. It's a partial derivative of this function with respect to x, the function that we have to find. So, and it is y. Okay, you can see. So what we do, we are going to find f. In order to find f, we will integrate both sides with respect to x. We integrate both sides with respect to x. we are having and as we are integrating with respect to x, so this y is going to behave with a constant, so it will be outside, so integrand of will become 1 obviously, so its integral will be x. So that's it. And some constant, and constant is going to be a function with respect to y, because its derivative with respect to x is 0, so that's why we just take this. We just call it equation number 1 here for our a's, and we can just close it in a box. Now what we do, we have to find the value of this constant thing. This is actually a constant. So what we do, we just differentiate both sides with respect to our y. We differentiate this equation 1 with respect to our y. So that's it. So df dawa f upon dawa y is actually our n. That's it. So over here we can put this x outside as a constant, so the derivative of y is 1, so over here simply x is left plus some derivative of this function, which is represented by h prime of y, and this is n, and n is it was what? It was something this. So I have to turn the page once again. So yeah, what is our n? Our n was this. Okay, so this is our n, x minus y sine y. All right. So x minus y sine y is our n, is equals to x plus this thing. All right. So this x and this x will get cancelled. This thing is equals to negative y sine y. Now you have to find h of y. So this is the derivative of h of y. So just in order to find h of y, simply we just integrate both sides of this thing with respect to our y. Okay. Alright, so this is it. So it's going to give us the same function back, the original form. And over here, what we do, we have to apply here nothing but the biparts. Okay, so we have to apply here the biparts process. You can also see the biparts video in the description box if you want to. Okay, so I'm going to take this thing as my, let us do the work a little bit here. I'm going to take this as my f, and this function integral part, the trigonometric part is going to be taken as g, and this polynomial part is going to be taken as y, and differentiate f with respect to this one, and integral of these things are going to be represented with capital G, so it is going to be minus cos of y. Okay, that's it. So we know the formula of the biparts. What is this? This is the formula of the biparts in general form. So we are now going to use this thing. Excuse me. And f dash y is 1 and g is minus cos y, so it will look something like this. So this shows that excuse me. And the integral of your cos y is simply sine y. Okay, so that's it, plus some constant, and I'm not writing constant here. So this is your hy. I'm going to put this value of h of y over here in this equation. It's going to give me xy plus h of y is this minus sine y, and this is your given function, required function, which is behaving as the solution of of what, of this non-exact differential equation that we discussed over here, this one. Okay, so I hope now the concept is clear in your mind to some extent. And if this video really helped you in getting the concept, I humbly request you to subscribe my channel and thumbs up this video, share this with your friends and learners, and if you're having any kind of feedback, either positive or negative, just put in the comment box below, and so that I could further improve the quality of my videos. Alright, so take good care of yourself. I'll see you soon in future with some better videos. Allah Hafiz.